Every atom in your body is being held together right now by something physicists still do not fully understand. Inside each proton, a storm of invisible particles called gluons fires back and forth millions of times per second. Gluons are the glue. They are the reason matter holds. And right now, some of the smartest people on Earth are finding results they cannot explain. We are going inside the proton. We are visiting a liquid that shocked the world, a formula that was supposed to be zero, and a machine being built to photograph something no human has ever seen. If you enjoy the journey, subscribe. Let's begin. Every solid thing you have ever touched, your phone, your desk, the ground under your feet, is mostly empty space. The atoms that make up those things are almost entirely hollow. The nucleus sitting at the center of each atom is tiny beyond imagination. If a single atom were the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line, and inside that marble, something extraordinary is happening every single instant. Protons and neutrons sit packed together inside the nucleus. They should repel each other. Protons carry positive electrical charge, and positive charges push away from other positive charges. You have seen this yourself if you ever tried to push two magnets together at the wrong ends. The force between them gets stronger the closer they get. So protons crammed together at point-blank range inside a nucleus should fly apart instantly. The whole thing should explode. Every nucleus in your body should have shredded itself apart the moment it formed. It has not. You are still here, and the reason is gluons. Gluons are force-carrying particles. Think of them like tiny messengers that shoot back and forth between quarks at blinding speed. Quarks are the even smaller pieces that build protons and neutrons, and gluons are the signals those quarks constantly trade with each other. Each signal carries the strong force, which is the most powerful force in nature. The strong force is roughly 100 times stronger than electromagnetism at close range. That is why it wins. That is why the nucleus holds. But here is the part that makes physicists uncomfortable. Gluons carry something called color charge. This has nothing to do with actual color. It is just a label physicists gave to a property that has no good comparison in everyday life. Color charge works in a way that electromagnetism simply does not. When you move two electric charges farther apart, the force between them gets weaker. With the strong force, the opposite happens. Pull two quarks apart, and the force gets stronger, like stretching a rubber band. Let them sit close together, and they almost float freely. This means quarks and gluons can never escape. They are permanently trapped. Every gluon that has ever existed has spent its entire life inside a larger particle, bouncing between quarks, never once breaking free into open space. Scientists have never directly seen a single isolated gluon. They only know gluons exist because of what particles do when they collide at high speed, and the debris tells a story. That debris has been telling a strange story for decades, and the closer physicists look, the stranger it gets. A proton was supposed to be a simple object, 3 quarks held together by gluons. Clean and predictable. That picture held for a long time. It let physicists build models that worked well enough, but as accelerators got more powerful and collisions got more precise, cracks started showing up in that simple picture. The debris from high-energy crashes did not match the predictions. Something inside the proton was more complicated than anyone had planned for. And it turned out the gluons were the problem. At higher energies, gluons do not sit still and behave. They multiply. 1 gluon splits into 2, 2 split into 4. The inside of the proton starts filling up. And if gluons can multiply without limit, then the simple 3-quark picture falls apart completely. What physicists discovered next changed how they thought about matter at the deepest level. Because the proton does not just get crowded, it gets strange. And the strangeness starts with a question nobody had thought to ask. What happens when the proton fills up? For most of the 20th century, physicists had a clean mental picture of the proton. 3 quarks, a few gluons holding them in place. The whole thing about the size of 1/4,000,000th of a meter across. A tidy little package. Textbooks drew it as 3 colored dots connected by springs. Students memorized it. It felt settled. The first cracks showed up when physicists fired electrons at protons at very high speed. The electrons bounced back at angles that did not match the 3-quark picture. Something inside was absorbing momentum that the 3 quarks alone could not account for. Physicists started measuring how much of the proton's total momentum each part carried. They expected the quarks to carry most of it. What they found stopped them cold. The 3 quarks carried only about half the proton's total momentum. The other half belonged to the gluons. Half. This was not a rounding error. This was a fundamental shift in how physicists had to think about matter. The gluons were not just the glue. And because gluons carry color charge, which means they interact with each other through the strong force, the inside of a proton turned into something much messier than 3 dots connected by springs. Picture a school hallway between classes, students moving in every direction. Crowded, loud, chaotic. Now imagine that every student in that hallway can also create a copy of themselves at any moment, and those copies can create more copies. That is closer to what is happening inside a proton. The gluons multiply constantly, they split and recombine, they create fleeting pairs of quarks and antiquarks that appear and vanish before any detector can catch them. The proton is a storm, not a structure. And here is where it gets harder to accept. The shape of that storm changes depending on how fast the proton is moving. This is confirmed by both theory and experiment. When a proton sits nearly still, the gluon activity inside it looks one way. As the proton accelerates toward the speed of light, the distribution of gluons shifts. At very high energies, the number of low-energy gluons climbs sharply. The proton does not have a fixed interior. Its inside rearranges depending on conditions outside. Scientists at Brookhaven National Laboratory confirmed something even stranger. The gluon density inside a proton does not just depend on speed. It fluctuates from one collision to the next, even at the same energy. 2 protons moving at exactly the same speed can have different internal gluon arrangements when they collide. The proton's interior is not fixed even from moment to moment. It flickers. This matters far beyond particle physics classrooms. Every calculation that predicts what a particle detector should see depends on knowing the proton's interior. If that interior keeps changing, every prediction carries more uncertainty than physicists have been assuming. Experiments at the biggest colliders on Earth rest on models of the proton, and those models were built on the tidy 3-quark picture. That picture is gone now. Physicists have been patching and updating their models for years, but the better their tools get, the more the proton surprises them. The flickering gluon storm inside is real. The confirmed measurements back it up, and that storm has a behavior that nobody fully predicted. At higher and higher energies, the storm grows. The gluons multiply faster than the models expected, and multiplication without a ceiling is a problem, because something has to stop it, and what stops it is one of the strangest ideas in modern physics. 1 gluon becomes 2, 2 become 4, 4 become 8. Keep going and the numbers get out of hand fast. This is not a metaphor. This is what confirmed physics says happens inside a proton when energy climbs. Gluons carry the strong force, and the strong force allows 1 gluon to split into a pair of gluons without violating any known law. The math permits it. The experiments confirm it. And as physicists pushed their colliders to higher and higher energies, they watched the gluon count inside protons climb far faster than the original models predicted. The process is called gluon splitting, and it feeds on energy. The more energy in the system, the more often splits happen. Each new gluon can split again. The rate of growth is steep. If you plotted the number of low-energy gluons inside a proton against the energy of the collision, the line does not rise gently, it shoots upward. Here is why this should bother you. A proton is not infinitely large. It has a definite size. You cannot keep cramming more and more gluons into the same tiny space without something happening. A classroom can hold 30 students comfortably. Pack in 300, and the situation changes. The students start bumping into each other. Movement becomes impossible. The rules of the room break down. The same pressure builds inside a proton. As the gluon count climbs, the gluons start crowding each other, and crowded gluons do not behave the same way as sparse ones. When two gluons overlap, they can merge back into one instead of splitting into more. The process that drives growth starts working against itself. This competition between splitting and merging is at the center of one of the biggest open questions in physics today. Scientists call the state where splitting and merging balance each other gluon saturation. It is a confirmed prediction of the theory, meaning the math demands it must exist. But pinning down exactly where and when saturation kicks in has proven extraordinarily difficult. The reason it matters so much is this. Gluon saturation, if confirmed in detail, would define a completely new regime of the strong force. A new state of matter in a sense, one where the rules shift. And the physics of that state would apply across all protons and all heavy nuclei at high enough energies. Every collision at every major accelerator on Earth would be affected. Every model would need updating. Physicists have been chasing saturation for decades. They have found strong hints. Experiments at major facilities have produced suppression patterns in particle debris that match what saturation would predict. Scientists at the Department of Energy highlighted one of these results in 2023, describing the suppression of back-to-back particle pairs as among the clearest signals yet seen. But the field has stopped short of declaring saturation fully confirmed. The evidence is strong, the proof is still being built. That is part of why the scientific community has been buzzing with unusual energy. A prediction this fundamental, sitting at the edge of confirmation for this long, is rare. Most predictions in physics get confirmed or ruled out within a few years. Saturation has lingered in a difficult middle zone for a generation. And here is the thing that keeps theorists awake at night. If saturation is real, and the evidence says it is, then the gluon storm inside a proton has a ceiling, a limit, a new kind of order hiding inside the chaos. Something is going to stop the growth, and what that something looks like has only recently started becoming clear. Imagine filling a bathtub. Early on, the water rises fast. Then you get close to the rim and it feels like it slows. The rate of filling does not change, but the available space does. Fill the tub past the rim and the water goes somewhere else, or it spills. The tub has a ceiling. Gluons hit a ceiling too. At high enough energies, a proton gets so packed with gluons that the rate of new gluons appearing equals the rate of gluons merging back together. Splitting and merging reach a balance. The gluon count stops climbing. The density levels off. This is saturation. And though the concept has been in the theory since the 1980s, finding direct proof in actual data has taken decades. The theory of saturation comes from quantum chromodynamics, the confirmed framework that describes the strong force. Within that framework, the math predicts that gluon density cannot keep growing forever. It must hit a wall. This wall is not a physical boundary. It is a dynamical one, meaning it emerges from the gluons interacting with each other, colliding, merging, and redistributing energy across the system. Finding that wall in data requires looking for specific signatures in the debris from particle collisions. One of the clearest predicted signatures involves pairs of particles that come out of a collision, moving in opposite directions. In a low-density proton, those pairs come out clean and back-to-back, like two billiard balls bouncing off each other in opposite directions. In a saturated gluon field, the dense tangle of gluons scrambles those pairs. They lose their clean opposite direction pattern. The signal fades. Scientists at major facilities have seen exactly this fading. The suppression of back-to-back pairs grows stronger as the collision involves heavier nuclei, which carry more gluons to begin with. The Department of Energy highlighted this pattern in 2023 as strong evidence for gluon recombination, the same process saturation predicts. The heavier the nucleus, the stronger the suppression. The data points in one direction. But here is the problem that keeps physicists honest. Multiple explanations can produce similar signals in the debris. Saturation is the leading candidate, but it is not the only one. Confirming saturation cleanly requires a machine that can probe gluon structure more directly, with far more precision than current colliders allow. That machine does not exist yet. It is being built, and understanding why it needs to exist starts with understanding how strange gluon behavior gets at extreme energies. One of the most striking confirmed results from the last 2 decades involved nuclear collisions where the gluon content of the nuclei was so high that the gluons had to be reshaping the geometry of the collision itself. Scientists described the gluon field inside a fast-moving heavy nucleus as resembling a flattened disk compressed by the extreme speed into a pancake-like sheet. The gluon density in that sheet is so extreme that it changes how every collision inside that nucleus proceeds. The proton's wall is real. The wall in a heavy nucleus is even more extreme. And the particles coming out of those collisions carry a message about what happens when gluons run out of room. That message took physicists years to decode. And one team in particular spent years building a model that finally described the interior of the proton as something stranger and more alive than anyone had expected. What they found changes everything about how the proton is pictured today. A team at Brookhaven National Laboratory was staring at a problem. Their collision data did not match their models. The discrepancy was not huge. It was subtle. But in physics, subtle discrepancies are the ones that matter most. A small gap between prediction and result means something is wrong with the picture. The standard picture of a proton said the gluon distribution inside it was relatively smooth and fixed. A stable cloud of gluons spread around the quarks in a predictable pattern. Plug in the energy, get out the distribution. Clean, simple, consistent. The Brookhaven team's data said otherwise. 2 protons at the same energy were not colliding the same way every time. The debris from hundreds of collisions at identical energies showed variations that a smooth, fixed gluon distribution could not explain. Something inside the proton was changing between collisions. The proton looked different each time. The team built a new model. In this model, the gluon density inside the proton does not stay fixed. It fluctuates. From one moment to the next, gluons cluster differently. Dense pockets form in one region, then shift. The pattern rearranges constantly, like a storm whose clouds move and thicken and thin from second to second. This confirmed model describes the proton's interior as a flickering gluon field, rather than a stable shell. The publication of this model changed how physicists talked about the proton. The flickering interior means that every proton-on-proton collision is slightly different from the last. Even at identical energies, the effective size and shape of the proton changes with each encounter. Some collisions hit a dense gluon pocket head-on, others glance off a less dense region. The result is a spread of outcomes that mirrors the spread seen in actual data. This is confirmed physics. The models that include gluon fluctuations produce results that match the data better than models that do not. The flickering is real, and that creates a problem that ripples outward from the proton into every major accelerator experiment on Earth. If the proton's interior changes moment to moment, then any calculation that assumes a fixed interior is working with an average picture. That average is useful, but it hides something important. It hides the extremes. It hides the collisions that hit an unusually dense gluon pocket and produce a burst of particles that looks nothing like the average. It hides the rare events, where the gluon distribution drops into an unusually sparse state, and the collision barely registers. The Brookhaven model gave physicists a tool to account for those extremes, but the deeper implication is harder to dismiss. The proton is alive in a way the textbook diagram does not show. It is not a fixed structure. It is a breathing, shifting, flickering field of gluon activity. different in each moment, different from each angle, different at each energy. And here is where things take a turn that most people outside of physics have never heard about. The fluctuations inside a single proton turn out to have consequences that appear in a completely different kind of experiment. Collisions that were supposed to be far too small to produce collective behavior started showing exactly that behavior. Something was organizing the debris from tiny collisions in ways that only massive collisions were supposed to produce. The proton's flicker was causing something nobody expected to see. Picture a small rock hitting still water. It makes a small ripple. Clean, circular, predictable. Now picture a handful of sand thrown at the water. You get chaos. Different grains hit different spots at different angles. The ripples interfere with each other. The surface becomes complicated. Proton collisions were supposed to work like the small rock. Clean, simple, predictable. The proton was small. The collision was fast. The result should have been a small, well-understood spray of particles flying outward. What physicists actually saw at the colliders was more like the handful of sand. The debris from proton-on-nucleus collisions showed patterns of organized flow. Particles coming out of the collision were not scattered randomly. They came out in correlated streams, almost as if the debris had been organized by something before it left the collision zone. This kind of organized flow had been seen before, but only in collisions between two heavy nuclei, where thousands of protons and neutrons slammed into each other and produced a massive, hot blob of matter. A single proton hitting a nucleus had no business producing that kind of organized behavior, but it did, and the flickering gluon field inside the proton became the leading explanation. Here is why. A proton with a fixed, smooth gluon interior hits a nucleus and produces a spray that matches simple predictions. A proton with a flickering, clumpy gluon interior hits a nucleus and deposits energy in uneven patches. Those uneven patches create pressure gradients. Pressure gradients push particles outward in organized streams. The clumpier the gluon distribution, the more organized the outgoing debris. Brookhaven confirmed that models including gluon fluctuations predict exactly the kind of organized flow physicists were seeing in small collision systems. The flicker was not just an internal property of the proton. It was printing its pattern into the outgoing debris. It was leaving fingerprints. This matters for a reason that goes beyond academic interest. Physicists running the large colliders need to know whether the organized flow they see in small systems comes from the proton's gluon structure or from the formation of a tiny blob of plasma inside the collision. Those two explanations predict different things. They require different theoretical tools, and they point to different conclusions about how matter behaves at extreme conditions. The debate between gluon structure and plasma formation is still open. The confirmed evidence favors gluon fluctuations as a major contributor, but plasma formation cannot be fully ruled out yet. The question sits in an uncomfortable place where both explanations fit the data to varying degrees. What physicists do agree on is this: the proton's interior, with all its flickering and rearranging, leaves marks on every collision it takes part in. Those marks change the readout of every particle detector on the planet. Every analysis that assumes a smooth, simple proton is operating with an approximation. And the more powerful the collider, the more the approximation breaks down. At the very highest energies that current machines can reach, the gluon content of a proton explodes upward. The multiplication rate outpaces everything. The inside of the proton is no longer just flickering. It is filling up. And what happens when it fills up is the question that changes the story entirely. Imagine you fire two pool balls at each other head-on. They hit, they bounce back in opposite directions. One goes left, one goes right. Clean, symmetric, predictable. That is what particle pairs do in low-density collisions. They come out back-to-back. Physicists call this back-to-back correlation. It is one of the cleanest signals in particle physics. When two particles come out of a collision moving in exactly opposite directions, It tells you the collision was simple and the gluon field they passed through was sparse. The signal stays clean because nothing tangled them up on the way out. Then scientists started running collisions with heavier nuclei. A heavier nucleus packs more protons and neutrons, which means more quarks, which means vastly more gluons. A gold nucleus, for example, contains 79 protons and about 118 neutrons. That is nearly 200 nucleons each, one packed with its own gluon storm. When a particle passes through a gold nucleus at high energy, it does not pass through a calm medium. It passes through a blizzard. And in that blizzard, the clean back-to-back signal fades. Physicists at the relativistic heavy ion collider at Brookhaven measured exactly this effect. In collisions involving lighter targets, the back-to-back pairs came out clean. As the target grew heavier and the gluon content climbed, the back-to-back correlation weakened. The heavier the nucleus, the more the signal disappeared. By the time the nucleus was large enough to carry the densest gluon fields, the back-to-back pairs were nearly gone. This is one of the strongest experimental hints at gluon saturation that physics has produced. The Department of Energy confirmed this pattern in 2023 as evidence consistent with gluon recombination. When gluons pile up and start merging, they scramble the trajectories of outgoing particles. The clean opposite direction signal gets washed out because the dense field has disrupted the simple geometry of the collision. The signal does not fade randomly. It fades in a specific way. The heavier the nucleus, the stronger the suppression. This scaling behavior is exactly what gluon saturation predicts. If something other than saturation were causing the fading, the scaling would look different. But here is the tension that makes physicists careful. The fading is consistent with saturation. That is not the same as proof of saturation. Proving it cleanly requires ruling out every other explanation that could produce the same suppression pattern. That work is ongoing. What the vanishing signal does confirm is that gluon density has a measurable impact on particle behavior. Dense gluon fields change the outcome of collisions in ways that sparse fields do not. The difference is real. The suppression is real. And the stronger that suppression gets, the closer physicists believe they are to finding the saturation boundary. The search for that boundary is about to get stranger, because when a heavy nucleus moves close to the speed of light, the gluons inside it do not just become dense. They change shape, and the shape they take is one of the most visually striking predictions in all of modern physics. Speed changes things. When you drive past a building at normal speed, it looks like a building, tall, wide, three-dimensional. If you somehow moved past that building close to the speed of light, the geometry of space itself would compress what you see. The building would appear flattened in the direction of your motion, thinner, more like a thin slab than a tower. Particles experience this compression too. When a proton or a heavy nucleus accelerates to nearly the speed of light, the space it occupies along the direction of motion gets compressed from the perspective of anything it is about to collide with. A gold nucleus moving at nearly light speed does not look like a sphere anymore. It looks like an extremely thin, extremely dense disk. The Department of Energy confirmed this picture and gave it a striking name. The gluon content of that fast-moving nucleus smears out into what scientists call a gluon pancake. The nucleus flattens. The gluons, which were distributed through a roughly spherical volume, get compressed into a thin sheet. Their density in that sheet becomes extreme. This is confirmed geometry, not just theory. The compression is a direct consequence of special relativity, the same physics that describes how time slows for fast-moving objects. As the nucleus speeds up, the compression increases. At the speeds reached inside the Large Hadron Collider at CERN, the flattening is so severe that a nucleus the width of a few femtometers in its rest frame becomes a disk thinner than any measurement humanity has ever made. And in that disk, the gluons are packed together more tightly than at any other known condition in the universe, except for the moments immediately after the Big Bang. The gluon pancake matters for every high-energy collision on Earth. When two heavy nuclei collide at those speeds, they are not two spheres smashing together. They are two gluon pancakes passing through each other at nearly light speed, each one so thin and so dense that the collision happens almost instantaneously. The pancakes overlap for a fraction of a second so small it has no useful comparison in everyday life. And in that moment, the conditions inside the overlap zone recreate something close to the state of the early universe. What comes out of that overlap is something physicists did not expect at all. They expected a hot gas. They built theories around a hot gas. They ran their colliders, looked at the data, and found something that had no right to be there. The debris from two gluon pancakes colliding did not behave like a gas. In 2005, a team working with the relativistic heavy ion collider published results that rewrote textbooks. The machine had been running for several years, smashing gold nuclei together at close to light speed. The collisions were producing temperatures tens of thousands of times hotter than the core of the Sun. At those temperatures, protons and neutrons were expected to dissolve. Quarks and gluons were expected to break free from each other and spread out into a hot, disordered gas. Physicists had a name for this state already: quark-gluon plasma. They had calculations predicting how it would behave. The gas was supposed to be weakly interacting, meaning the quarks and gluons inside it would barely notice each other, moving almost freely through the superheated volume. The data disagreed. The particles coming out of the collisions were not moving randomly the way gas particles would. They were organized. They were flowing. The debris showed patterns that physicists recognized from fluid dynamics, not from the behavior of weakly interacting gases. The matter produced in the collisions was flowing like water around obstacles, forming organized currents, following the contours of the collision zone in a way only a strongly interacting liquid could. The quark-gluon plasma existed. That part was confirmed. But it was the most perfect liquid ever measured in a laboratory. Its resistance to flow, what physicists call viscosity, was lower than any liquid measured before or since. Closer to zero viscosity than anything on Earth, liquid helium, the coldest natural liquid on the planet, flows with almost no friction, but the quark-gluon plasma beat it by a significant margin. This was deeply unexpected. The calculations said weakly interacting gas. The experiment produced the most frictionless liquid in the known universe. The surprise had a specific implication. If the quarks and gluons were interacting strongly enough to form a near-perfect liquid, then the simple picture of a hot gas of almost free particles was wrong. The strong force between gluons, even at those extreme temperatures, was powerful enough to keep the mediums strongly coupled. The gluons were not behaving like free particles, even when liberated from individual protons. They were still entangled with each other through the strong force. This confirmed result changed the field. It forced physicists to update their models of how quark-gluon plasma works. It changed how researchers interpreted every heavy ion collision result that came before and after, and it raised a question that nobody had seriously considered before. If the quark-gluon plasma produced in the collider is a near-perfect liquid, what does that say about the early universe? Because a fraction of a second after the Big Bang, the entire universe was quark-gluon plasma. For a brief instant after the Big Bang, the universe was smaller than a grapefruit. Every particle that would eventually become every star, every planet, every atom in every living thing existed in that tiny, unimaginably hot space. The temperature was so extreme that quarks and gluons could not bind together into protons and neutrons. Matter, as we know it, did not yet exist. The entire universe was a single roiling blob of quark-gluon plasma. Physicists used to picture that blob as a hot, chaotic gas, weakly interacting, particles zipping past each other without much entanglement. The gas cooled as the universe expanded. Quarks and gluons eventually stuck together into protons and neutrons. Protons and neutrons formed nuclei. Nuclei captured electrons and became atoms. Everything we see today grew from that cooling. The collider results changed this picture in a fundamental way. If the quark-gluon plasma produced in laboratory collisions behaves as a near-perfect liquid, and the early universe was also quark-gluon plasma, then the early universe was also a near-perfect liquid. It flowed. It had currents. It organized itself the way fluids do, with ripples and pressure waves moving through it. This is a confirmed shift in how cosmologists think about the universe's first microseconds. The ripples in that early liquid left imprints. As the plasma cooled and matter formed, those ripples became slight variations in density. Slightly denser regions pulled in more matter through gravity. Over billions of years, those slight variations grew into the large-scale structure of the universe. Galaxies, galaxy clusters, the vast web of filaments and voids that spans hundreds of millions of light-years. The pattern of the universe today carries the memory of a liquid. The web of galaxies maps, in some sense, onto the ripples that moved through a hot gluon fluid a fraction of a second after everything began. And here is the piece that makes this deeply personal, rather than just abstract. Every atom in your body passed through that liquid. The protons in your cells were forged in the moments after the plasma cooled. Your existence is downstream from a near-perfect fluid that no human laboratory has ever fully reproduced, though the collider came extraordinarily close. The quark-gluon plasma result was confirmed, dramatic and world-altering. But it also opened a new problem, because while the collisions between two large nuclei were producing this liquid as expected, a smaller and stranger experiment started showing behavior that had no clean explanation. Collisions that were far too small to produce a significant volume of plasma were producing signals that looked organized, signals that looked like flow, signals that looked almost like the liquid. Something small was doing something that only something large was supposed to do. The rule seemed simple. A large collision produces large effects. Smash two heavy nuclei together and you get a hot flowing liquid. Smash a single proton into a nucleus and you get a clean, simple spray of particles. One is a thunderstorm, the other is a raindrop. The raindrop was not supposed to make waves, but when physicists analyzed data from proton-on-lead nucleus collisions at the Large Hadron Collider and proton-on-gold nucleus collisions at the Relativistic Heavy Ion Collider, they found something that violated the simple rule. The debris from these small collisions was flowing. The particles coming out were correlated in ways that looked organized. Streams of particles emerged at specific angles relative to each other in patterns that matched the kind of collective flow seen in large nucleus-on-nucleus collisions. A single proton hitting a large nucleus was producing a hint of collective behavior. This should have been impossible under the old picture. Collective flow in large collisions comes from many particles interacting in a shared medium, building up pressure, then releasing it in organized bursts. A single proton was too small to create that medium. It carried too few quarks, too few gluons, to generate enough shared interaction to organize the debris. And yet the data showed organization. Two explanations competed immediately. The first said that even a single proton could, under the right conditions, create a tiny but real droplet of quark-gluon plasma in its collision with a nucleus. A miniature plasma lasting an unimaginably short time, but real enough to generate collective flow before it evaporated. The second explanation said no plasma was needed. The flickering, clumpy gluon distribution inside the proton was already organized enough to stamp its structure onto the collision and produce debris that looked like flow without actually being flow from a plasma. Both explanations fit the data. Both are still being debated. What the result confirmed, regardless of which explanation is correct, is that the interior of the proton has a structure complex enough to shape collisions in ways physicists had not fully accounted for. The gluon distribution inside a proton is not a passive background, it is an active ingredient that changes the outcome. And here is the part that makes physicists genuinely uncertain. If even tiny collision systems can produce collective-looking behavior, then the boundary between small and large, between simple and complex, between raindrop and storm, is not where anyone thought it was. The behavior that was supposed to require a massive, hot, strongly interacting medium might have a simpler gluon-based explanation sitting right inside the proton. Figuring out which explanation is right matters enormously. It determines whether physicists are studying tiny plasmas or gluon geometry when they analyze small collision systems. The two possibilities demand completely different theoretical frameworks and different experimental tools to test. And while that debate continued, something even stranger was waiting, because the same scientists studying those small collisions found a pattern in heavy nuclear collisions that pointed back to something universal, something that connected gluon physics to the deepest mathematical structures in all of theoretical physics. Science rarely settles questions quietly. When two strong explanations compete for the same data, physicists do not flip a coin. They design new experiments, new measurements, new tests specifically built to pull the two explanations apart. And when two explanations make the same prediction for every existing measurement, the fight can go on for years. That is exactly where the field of small system collisions sits today. On one side, the plasma camp. These physicists argue that even a proton-on-nucleus collision can produce a tiny droplet of quark-gluon plasma, a droplet so small it would fit inside a proton with room to spare, lasting for such a short time that no clock could measure it. But real, and real enough to organize the debris before it evaporates. The flow patterns seen in the data are, in this view, genuine collective motion inside a miniature liquid. On the other side, the gluon geometry camp. These physicists argue that no plasma is needed. The proton's internal gluon distribution, with its flickering, clumping, fluctuating structure, is itself already organized enough to create the observed patterns. When that structured gluon field hits a nucleus, it imprints its geometry onto the collision. The outgoing particles reflect the shape of the gluon distribution, not the hydrodynamics of a liquid. Both camps have published models that match the data. Both have found measurements that favor their view. Both have also found measurements that their rival explains equally well. The fight is real, ongoing, and unresolved. What makes this scientifically important is not the competition itself, it is what the competition reveals about the limits of current detectors and colliders. The existing machines do not have enough precision to make a measurement that cleanly separates the two predictions. Every result so far has been ambiguous enough that both camps can claim partial support. This is rare. Most open questions in particle physics have at least one measurement that leans clearly in one direction. The small collision problem has resisted that kind of clarity for over a decade, and the reason it has resisted is directly tied to the same underlying challenge that runs through every chapter of the gluon story. The gluon distribution inside a proton is not fully mapped. Its fluctuations are not fully characterized. Its geometry changes with energy, with nucleus size, with angle, with speed. Every model that describes small collisions has to make assumptions about that interior, and those assumptions are exactly what the competing explanations disagree about. This is why the next generation of experiments matters so intensely. The arguments between the plasma camp and the gluon geometry camp cannot be settled with current tools. They require a machine that can directly probe the gluon interior, map its distribution, measure its fluctuations, and remove the assumptions that both camps currently rely on. That machine has a name, it has a location, it has a budget, and a construction timeline. But before it can settle the small collision debate, it has to tackle an even bigger target, one that has been hanging over all of gluon physics for decades. The saturation boundary. The word saturation sounds ordinary. Fabric soaked with water, a color pushed to its maximum intensity, a market where no new buyers exist. In everyday life, saturation just means full. Inside a proton at high energy, saturation means something far stranger. When gluon density climbs high enough that merging happens as fast as splitting, the proton enters a new regime. The rules that govern sparse gluon fields stop applying. The mathematics changes. The behavior of every particle that passes through that dense field changes with it. Saturation is a genuine phase of the strong force, as distinct from normal gluon behavior as ice is from liquid water. This is a confirmed prediction of quantum chromodynamics. The equations demand that saturation exists. What remains unknown is exactly where the boundary sits, which energies and which nucleus sizes push a system into the saturated regime, and what the interior of that saturated state looks like in detail. Here is what makes saturation strange. A saturated gluon field is nearly opaque. Particles trying to pass through it scatter off the dense gluon tangle almost immediately. Nothing gets very far inside before interacting. This opacity is measurable. It produces specific signatures in the debris of high-energy collisions, and those signatures have been building up in experimental data for years. The Department of Energy highlighted in 2023 that collisions involving heavier nuclei showed suppression patterns consistent with gluons recombining, which is the same process that defines the saturated state. The pattern scaled with nucleus size exactly as saturation theory predicts. Lighter nuclei showed weaker suppression. Heavier nuclei showed stronger suppression. The trend pointed straight at saturation as the explanation. But the most important thing about saturation is what it says about universality. Saturation theory predicts that every proton and every nucleus at high enough energy will reach the same regime. The details of the specific nucleus stop mattering once the density gets high enough. The gluon field takes on a universal character, described by a single scale called the saturation scale, that applies across all strongly interacting matter at extreme energies. If saturation is universal, then it defines the behavior of matter in every high-energy collision on Earth. Every experiment at the Large Hadron Collider, every future measurement at the next generation of accelerators, every collision that recreates the conditions of the early universe, all of it sits on top of a saturation regime that determines the initial conditions. Getting saturation wrong means getting all of it wrong. This is why physicists describe it as one of the central open questions in nuclear physics. The stakes are that high, and the confirmation they have been waiting for depends on an experiment that nobody has been able to run yet. An experiment that requires firing an electron at a proton or nucleus at precisely the right energy, measuring the gluons directly, and mapping the interior of the proton with a resolution that current machines cannot reach. That experiment is coming. The machine that will run it is under construction right now. But before we get there, something else happened. Something that came from a completely different direction and shook the community in a completely different way. A formula that every physicist in the field had treated as dead came back to life. The year was 2001. The relativistic heavy ion collider in Brookhaven, New York, switched on and began smashing gold nuclei together at energies no machine had reached before. Physicists gathered around their data feeds, expecting confirmation. They had their models, they had their predictions. The quark-gluon plasma was supposed to behave like a hot gas, weakly coupled, particles moving almost freely through the superheated volume. The first results were puzzling. The debris did not match the predictions well enough to feel comfortable. Particles that should have passed through the plasma with minimal interference were being stopped. Jets of particles that should have emerged cleanly from the collision were suppressed. High-energy particles were losing energy at a rate that did not fit a weakly interacting gas. A team published a paper in 2002. Existing models struggled to explain the particle behavior they were seeing. The gap between prediction and data was too large to shrug off. Something fundamental about how the collision was working was different from every theoretical expectation. Physicists reacted the way they always do when data breaks a model. They went back to the equations. Over the next several years, new frameworks were built. New models of the plasma emerged, ones that treated it as strongly coupled rather than weakly interacting. The hydrodynamics of a near-perfect liquid with almost zero viscosity. By 2005, the case for a strongly interacting liquid was strong enough that a major journal published the results, and the physics community accepted the update. But the early discrepancies had already done their damage to the simple picture. The collider had fired up expecting confirmation of a clean theory and had instead opened a list of new questions. The plasma was real, the liquid was real, and the fact that it was a liquid and not the expected gas meant that every previous calculation about how high-energy nuclear collisions worked needed to be revisited. That revisiting is still happening. The relativistic heavy ion collider ran for over 2 decades before winding down its main gold-on-gold program. In that time, it produced results that transformed the field. It confirmed the liquid it produced hints of gluon saturation. It found that small collisions behaved in ways large ones were not expected to share. It raised question after question faster than theorists could answer them. And it left one specific mystery sitting right at the edge of what any current machine can measure. A mystery that involves the gluon interior of the proton directly. A mystery that only a machine designed specifically to see gluons can crack. The collider showed where the questions live. It could not go inside to answer them. Something strange was hiding inside the proton, and the tools to find it were still being designed. Physicists have never seen a gluon directly. Every piece of evidence about gluon behavior comes from what particles do after a collision, the spray of debris that fans out through the detectors, each particle carrying information about what happened in the microsecond of impact. Reading that debris is like reading the impact site of a car crash to reconstruct what the two cars looked like before they hit. You do not have the cars anymore. You have crumpled metal, shattered glass, skid marks, and the positions of every piece. From all of that, you build backward to figure out what was there. Physicists call this kind of analysis deep inelastic scattering. A high-energy particle, usually an electron or a proton, fires into a target nucleus. The collision is violent enough to knock quarks and gluons loose from their normal positions. The collision products spray outward through the detector. Each particle carries a record of the momentum it absorbed in the collision. By measuring the angles and energies of every outgoing particle, physicists reconstruct which part of the proton the incoming particle hit, how much momentum that part was carrying, and how the collision products reorganized after the impact. From hundreds of millions of these collisions, they build a statistical picture of the gluon distribution inside the proton. That picture has a name: the parton distribution function. It maps out how the proton's momentum is divided among its quarks and gluons at a given energy. The gluon distribution specifically shows how many gluons carry a given fraction of the proton's total momentum, and how that distribution shifts as the collision energy climbs. This is confirmed science. The parton distribution function has been measured across decades and across multiple facilities. It has been refined with every new generation of experiment, and one of its most striking features is what happens to the gluon distribution at low momentum fractions. As the energy of the collision rises, the number of low momentum fraction gluons explodes. The gluon distribution shoots upward. The proton appears to be filling with slow gluons. This is the multiplication process described earlier, now visible directly in the data. And the question the data cannot yet answer is whether that explosion of gluons ever hits a ceiling. The current measurements extend to high energies, but the precision drops off exactly where saturation is predicted to kick in. The existing data are consistent with saturation. They are also frustratingly consistent with a proton that has not quite reached the saturated regime yet, but is approaching it. Distinguishing between those two possibilities requires measurements at higher energies, with a type of probe that can resolve the gluon distribution with far more spatial detail than current colliders provide. An electron fired at a proton provides that kind of probe. Electrons are point-like. They interact electromagnetically. They can resolve the gluon distribution with a precision that two protons smashing together cannot match, because two protons bring too many messy strong force interactions that obscure the signal. An electron-on-proton collider could map the gluon interior with the clarity that decades of indirect measurement have failed to achieve. That is precisely the machine currently being constructed, and the story of why it took this long to build is a chapter in itself. One of the cleanest tools in nuclear physics is scaling. If a physical effect is real and driven by the mechanism you think it is, the effect should scale predictably with the conditions you control. Change the nucleus size and the effect should change in a specific way. If the suppression of back-to-back particle pairs comes from gluon density, then heavier nuclei should suppress those pairs more strongly. Each added nucleon brings more gluons. More gluons means denser fields. Denser fields means more scrambling. That is exactly what the data shows. Experiments at the relativistic heavy ion collider and at CERN studied collisions where a proton or deuteron, which is a nucleus made of just one proton and one neutron, struck nuclei of increasing size. From light targets like carbon all the way up to heavy gold nuclei, the team measured the back-to-back particle pair suppression at each step. The pattern was consistent and striking. The suppression grew steadily with nucleus size. Light nuclei showed mild suppression. Heavy nuclei showed far stronger suppression. The heaviest nuclei produced the weakest back-to-back signal of all. The trend held across collision energies and across different detector configurations. This scaling behavior is a signature that gluon recombination predicts. In a sparse gluon field, back-to-back pairs form and exit cleanly. In a dense recombining gluon field, the pairs scatter off the gluon tangle and lose their clean correlation. The denser the field, the weaker the correlation. Heavier nuclei carry denser fields, so heavier nuclei suppress the signal more. The mathematics of this relationship is specific and was written down before the experiments ran. The data matched the prediction. The Department of Energy highlighted this result as one of the strongest experimental cases yet for gluon saturation emerging from particle collisions. The language used was careful, as it should be in science. The result was described as strong evidence consistent with gluon recombination, and the trend was described as pointing toward the saturation regime. Here is why the careful language matters. The scaling pattern is necessary for gluon saturation to be correct, but it is not sufficient to prove it exclusively. Other mechanisms can also suppress back-to-back pairs in heavy nuclei. The scaling matches saturation theory beautifully. It does not rule out every alternative. This is a pattern that runs through the entire history of gluon saturation research. Each new result fits. Each new result moves the field closer, and each new result stops just short of the final confirmation, because the existing tools cannot reach deep enough into the gluon interior to measure what they need. The confirmation requires resolving not just the suppression pattern, but the spatial structure of the gluon field that causes it. That requires a probe that can see inside the proton with a resolution no current machine can match. What recently emerged from an entirely different direction, though, was something that nobody had planned for: a connection between gluon saturation and one of the most universal mathematical patterns in all of physics. And the discovery of that connection came from a direction that surprised everyone. Deep inside the mathematics of the strong force, physicists found something they did not expect: a pattern. And the pattern was not unique to gluons or to the strong force. The same mathematical structure appeared in other areas of physics, so different from nuclear collisions that the connection seemed impossible at first. The discovery came from theorists. In 2025, the Department of Energy highlighted work showing a link between gluon saturation and a concept called asymptotic symmetry. Asymptotic symmetry is a set of mathematical rules that govern how particles behave when they ascend to infinite distances, or when energies go to extreme limits. The same class of symmetries had already appeared in gravitational physics, in the study of black holes, and in efforts to understand how information escapes from extreme gravitational fields. Finding those same symmetries inside the gluon saturation problem was striking enough to be worth highlighting as a major result. Here is the core idea in plain terms. When a large number of gluons pile into the saturation regime, the system takes on a kind of universal behavior. The specific details of the nucleus stop mattering. The specific configuration of the gluons stops mattering. What remains is a system governed by the saturation scale, a single number that determines everything about how the dense gluon field behaves. The system has lost its memory of where it came from. That loss of memory is a form of symmetry, and that symmetry, it turns out, belongs to the same family of mathematical structures that appear in gravitational physics and quantum field theory at extreme limits. This is a confirmed mathematical result. The connection between gluon saturation and asymptotic symmetry has been established in the theory. What it means for the physical understanding of gluons is still being worked out. But the existence of the connection hints at something deeper. The strong force at high gluon density may not be an isolated curiosity. It may be part of a broader set of universal laws that cut across different forces and different scales. If that is true, understanding gluon saturation would contribute to understanding physics far beyond nuclear collisions. It would connect the behavior of the smallest studied objects in the universe, the gluon fields inside protons, to the behavior of some of the largest, including black holes, and the structure of space itself. This is a theory. The connection is mathematically real and confirmed. Whether it has deep physical consequences is the question the community is now pressing forward to answer. And pressing forward requires a machine built for one purpose: to see the gluon distribution directly, with enough precision to confirm saturation, map the saturation scale, and test whether the universal behavior predicted by asymptotic symmetry actually appears in the measured data. Construction has already started, and what this machine is designed to do is unlike anything ever attempted before in nuclear physics. There is a facility being built right now on Long Island, New York, at Brookhaven National Laboratory, that physicists have been arguing for and dreaming about for over 2 decades. It is called the Electron-Ion Collider, and its entire purpose, its reason for existing, is to photograph gluons. Every measurement of the gluon interior discussed so far has been indirect. Physicists fired particles at protons, watched the debris, and worked backward. They read the crash site. The Electron-Ion Collider changes the method entirely. Instead of 2 protons or 2 nuclei smashing together in a chaotic strong force collision, the new machine fires electrons at protons and nuclei. Electrons are point-like. They carry no color charge. They interact electromagnetically, which is a far cleaner, more controlled interaction than the strong force. This matters enormously. When a proton collides with another proton, both of them bring strong force interactions that muddy the data. Quarks and gluons from both sides interact simultaneously. The collision is a storm hitting another storm. Untangling what came from which particle is a serious challenge that limits precision. When an electron hits a proton, the electron is a clean probe. It does not carry quarks or gluons of its own. It bounces off the quarks and gluons inside the proton through a well-understood electromagnetic interaction. The recoil of the electron tells physicists exactly how much momentum it transferred and to which part of the proton. The measurement is precise in a way that proton-on-proton collisions simply cannot be. The Electron-Ion Collider pushes this further by varying the energy of the electron and the energy of the proton or nucleus independently. This gives physicists a dial they can turn. They can scan through energy systematically, mapping the gluon distribution at each step. They can look for the exact energy where saturation begins by watching how the distribution changes as the dial turns. The gradual climb, then the leveling off. The saturation ceiling should become visible in the data in a way that no previous machine could show. The machine is also designed to measure the spatial distribution of gluons. not just their momentum distribution. Previous experiments could measure how many gluons carry a given fraction of the proton's momentum. The electron-ion collider will also measure where those gluons are located inside the proton, building a three-dimensional map of the gluon interior rather than a one-dimensional momentum snapshot. This three-dimensional imaging is what physicists call tomography. It is the particle physics equivalent of a medical scan, and it will produce the first detailed pictures of the interior of a proton that include the gluon structure directly. The Department of Energy in Brookhaven described the machine as a true gluon imaging instrument. That language is unusual for a particle physics facility. Most accelerators are general-purpose tools that address many questions at once. The electron-ion collider has been designed with gluon physics as its central scientific target, with saturation confirmation and three-dimensional proton imaging as its defining goals. Construction is underway. The machine is expected to begin taking data in the mid-2030s, and the community's anticipation is not just about saturation. The electron-ion collider will also test the asymptotic symmetry connection, probe the flickering gluon fluctuations that Brookhaven's theoretical models predicted, and weigh in on the small collision debate between plasma formation and gluon geometry. It is being built to answer the hardest open questions in gluon physics, all at once. But while the machine is being constructed, a completely separate shock hit the community, and it came from a direction nobody expected. Close your eyes and picture a proton. Most people imagine a sphere, 3 dots inside, the quarks, connected by lines, the gluons. The textbook diagram, clean, simple, static. That picture is about as accurate as drawing Earth as a perfectly smooth ball. Useful for some purposes, deeply misleading for others. The three-dimensional image that the electron-ion collider is designed to produce will look nothing like the textbook sphere. Based on everything physicists already know from existing data and theoretical models, the image of a proton's gluon interior will look more like a storm system viewed from above than a clean geometric shape. The gluon density is highest at the center and falls off toward the edges, but the drop-off is not smooth or symmetrical. Brookhaven's flickering gluon models predict that the density varies across the proton's face in ways that change from moment to moment. The electron-ion collider will not capture a single frozen snapshot. It will build a statistical picture from millions of collisions, averaging the flickering into a distribution that shows which regions are most likely to be dense and which are most likely to be sparse. That statistical picture will reveal something specific that current measurements cannot: the shape of the gluon distribution as a function of position, energy, and nucleus size simultaneously. Physicists call this the Wigner distribution, and it is the most complete possible description of where gluons are and what they are doing inside the proton. No existing machine has the precision to measure the Wigner distribution directly. The electron-ion collider is designed specifically to reach it. What the picture would show, according to current theoretical expectations, is a proton that is denser at low energies and more uniformly saturated at high energies. At low energies, the gluon storm has pockets of density and pockets of emptiness. At high energies, saturation smooths those pockets out. The saturated proton looks more uniform than the unsaturated one, a counterintuitive result that comes from the merging process that prevents further growth. For heavy nuclei, the picture changes again. A gold nucleus at high energy is not just one saturated proton scaled up. It is a collection of flickering proton and neutron gluon fields overlapping and interacting. The gluon pancake geometry described earlier means that the image of a fast-moving gold nucleus would look like an extraordinarily dense, thin disk with a gluon distribution far more uniform than any single protons. Capturing that image would confirm saturation, map the saturation scale, and test whether the universal behavior predicted by asymptotic symmetry actually appears in the spatial distribution of gluons inside real nuclei. The scientific payoff of that measurement would ripple outward through physics for decades. But the electron-ion collider is still years from completion. The community working on gluon physics has not been standing still, and in 2026, a result arrived that nobody in the field had been expecting. It came from a formula that had been sitting in the physics literature for decades, treated as solved, filed away, and never revisited, until someone fed it to an artificial intelligence and asked it to keep thinking. Every particle interaction in quantum field theory can be calculated as an amplitude. Think of an amplitude as a number that tells you how likely a specific interaction is to happen. High amplitude means the interaction happens often. Zero amplitude means it cannot happen at all. Physicists calculate amplitudes using sets of rules developed over decades. These rules assign mathematical contributions to every possible way a group of particles can interact. For gluons, these rules belong to quantum chromodynamics. They are well established, widely used, and tested against experimental data continuously. For a specific configuration of gluons, all moving in nearly the same direction, and all carrying the same type of polarization, a particular amplitude had been calculated long ago and found to be zero. Physicists call this configuration the all plus helicity amplitude. When all the gluons are aligned in this specific way, the calculation gives zero. The interaction is forbidden. Physicists treated this as a settled result and moved on. It stayed settled for decades. Textbooks did not dwell on it. Researchers working on gluon scattering did not revisit it. A zero is a zero. There was nothing to explore. Then two things happened. A researcher at the Institute for Advanced Study noticed that the zero result relied on a specific assumption about the gluon configuration. The gluons were assumed to be moving in generic directions, with no special geometric relationship to each other. When that assumption held, the amplitude was zero. But what if the gluons were pushed into a nearly collinear configuration, meaning almost perfectly aligned along the same direction of travel? The assumption breaks down, the calculation changes, and the question nobody had seriously asked was, does the zero survive when the gluons are nearly collinear? The researcher had a tool available that previous generations of physicists did not, an artificial intelligence capable of reasoning through complex mathematical patterns for extended periods. Feeding the problem to the system and letting it work produced something unexpected. When the gluons were pushed into the nearly collinear configuration, the amplitude that had been treated as permanently zero became non-zero. A number came out of the calculation, where everyone had assumed only zero could live. The Institute for Advanced Study reported this result. Science magazine covered it, and the particle physics community had to reckon with something genuinely surprising. A result that everyone had considered closed for decades had just been reopened by a combination of human insight and machine reasoning. The full implications were still being worked out, but the direction was clear. Something that had been filed away as impossible was back on the table, and what came next in the verification of that result added another layer of strangeness to the story. The prompt went in, the system began working. What the researcher at the Institute for Advanced Study wanted to know was whether the all plus helicity amplitude for gluon scattering, the one that everyone treated as zero, had some surviving structure when the gluons approached a collinear configuration. The question was mathematical. The answer required working through layers of quantum field theory calculation that would take a human physicist weeks to unpack carefully. The artificial intelligence worked on it for 12 hours. 12 hours of continuous reasoning, checking, rechecking, and building toward an answer. At the end of that process, the system produced a formula, a non-zero expression for the gluon amplitude in the collinear limit. The formula was compact. It had a structure that human physicists could read and recognize, and it pointed toward a result that the field had not seen before. This is confirmed. Science magazine and the Institute for Advanced Study both reported this process. The artificial intelligence did not discover physics on its own. It did not invent a new theory. It performed an extended mathematical reasoning task, one that required holding many simultaneous constraints in mind across a long calculation, and produced a result that human researchers then had to verify by hand. The verification process is what makes the story scientifically meaningful. A formula produced by a machine, however sophisticated, carries no authority until human physicists independently confirm it through their own methods. The Institute for Advanced Study researchers did exactly that. They took the formula the system had produced and derived it analytically, using the established tools of quantum field theory to check whether the result was correct. It was correct. The artificial intelligence had found a genuine mathematical result in particle physics, a result that had been missed for decades because the community had accepted the zero and stopped looking. The machine found what decades of human attention had passed over, not because it was smarter than physicists, but because it could sustain focused mathematical reasoning on a specific narrow problem for 12 uninterrupted hours without getting bored or moving on. The Science magazine headline called it a surprising insight in particle physics. The Institute for Advanced Study described it as reopening a problem many theorists had effectively filed away. The language in both reports was careful, but the message was clear. Something new had appeared in gluon physics from a direction nobody had anticipated. And the result was not just mathematically interesting. It had practical consequences for how physicists calculate what happens when gluons collide. Those consequences reach into every major particle physics experiment on Earth. The all plus helicity amplitude being non-zero in the collinear limit sounds technical. The consequences are anything but technical. Gluons' scattering amplitudes are the foundation of every prediction that involves gluons. When physicists run a collider and want to predict what particles should appear in the detector, they calculate amplitudes for all the possible interactions inside the collision. Those calculations add up contributions from many different gluon configurations. If one configuration that was assumed to contribute zero actually contributes a non-zero amount, every calculation that included that assumption carries a small error. The error may be small. In most collision conditions, the collinear configuration is rare, and the non-zero amplitude is a correction, not a dominant term. But small errors in fundamental calculations have a way of becoming important exactly where the physics is most interesting. Near the saturation boundary, where gluons are nearly parallel and dense, the collinear configuration becomes far more common. The correction stops being small. The amplitude that was assumed zero becomes a meaningful contribution. This means the result matters most precisely in the regime that physicists are most urgently trying to understand, the high-density near-saturation regime, where the electron-ion collider will be taking data. The Institute for Advanced Study confirmed this. The mathematical result reopens a problem that had been treated as closed, and it does so in the regime most relevant to the pressing open questions in gluon physics. The timing of the result, just as the field is ramping up toward the electron-ion collider era, is scientifically significant. For physicists building predictions of what the electron-ion collider will see, the result means those predictions need to be checked against the new amplitude. Any calculation that assumed the all-plus configuration contributes zero needs to be revisited for the energy range where collinear gluons become common. The work is being done. What the artificial intelligence found was a gap. Not a catastrophic gap, but a real one. A place where an assumption had gone unchallenged for so long that it had become invisible. The machine's advantage was exactly that it had no memory of the assumption being settled. It approached the calculation fresh without the preloaded belief that zero was the only answer. This is a lesson the physics community is absorbing right now. Artificial intelligence, used as a mathematical reasoning tool on well-defined problems, with human oversight, can recover results that the field has missed. It is not a replacement for physical intuition or experimental creativity. It is a tool for finding what patient, sustained calculation can find when given a long enough run at a specific problem. the field has taken notice. And the deeper consequence of the result connects back to a property of gluons that makes them unlike any other particle in physics, a property called color charge, which has been mentioned several times but deserves its own full examination. Because color charge is the reason gluons behave in ways that nothing else in the universe does. Every force in nature has a carrier particle. Photons carry electromagnetism. The W and Z bosons carry the weak force. Gravitons, if they exist, would carry gravity. And gluons carry the strong force. But gluons are different from all the others in one fundamental way. The other force carriers do not carry the charge associated with their own force. A photon carries no electric charge. It transmits electromagnetic interactions between charged particles, but is itself electrically neutral. A graviton carries no gravitational mass in the usual sense. Gluons carry color charge. Color charge is the property that makes quarks interact through the strong force. There are 3 types of color charge, called red, green, and blue. These names mean nothing visual. They are labels for a property that has no everyday equivalent. Quarks carry 1 color charge each. Gluons carry 2, 1 color and 1 anticolor simultaneously. Because gluons carry color charge, they interact with each other through the strong force. Photons do not interact with other photons because photons carry no electric charge. Gluons interact with other gluons because gluons carry color charge. This single difference explains almost everything strange about the strong force. It explains why gluons split. One gluon can emit another gluon, the way a charged particle can emit a photon, but unlike the photon case, the emitted gluon is also a carrier of the same force. The multiplication cascades. It also explains why gluons can merge. 2 gluons can combine into 1. The splitting and merging processes are both allowed precisely because gluons carry the charge of their own force. It explains confinement. The strong force does not weaken with distance the way electromagnetism does. Pull 2 quarks apart, and the gluon field between them stretches. The energy in the stretched field grows. Eventually, the energy is high enough to produce a new quark-antiquark pair from the vacuum. The new quarks attach to the ends of the broken field. You can never isolate a single quark or gluon in empty space. Color charge is always confined inside a larger, color-neutral particle. It explains why the proton's interior is a storm. Gluons interact with quarks and with each other constantly. The inside of the proton is not 3 quarks sitting calmly. It is a turbulent web of quarks, gluons, and momentary quark-antiquark pairs, all interacting through color charge in a space smaller than 1 quadrillionth of a meter. Color charge is also why quantum chromodynamics, the theory that describes all of this, is so much harder to calculate with than electromagnetism. The interactions between force carriers, gluon-on-gluon scattering, create a level of mathematical complexity that electromagnetism simply does not have. And that mathematical complexity is what makes results like the non-zero collinear amplitudes so important. Every simplification that holds for gluon calculations is precious. Every assumption that turns out to be wrong creates work across the entire field. Color charge is what makes gluons the most complicated and most interesting particles in the Standard Model. And one of its deepest consequences is a phenomenon that still surprises people when they first hear it. Take a bar magnet, cut it in half. You do not get a north piece and a south piece. You get 2 smaller magnets, each with its own north and south. Cut again. Same result. No matter how many times you cut, you cannot isolate a single magnetic pole. Quarks and gluons work the same way, but more extreme. Try to pull a quark out of a proton, and the gluon field between the quark and its partners stretches. The field stores energy as it stretches, like a rubber band. Unlike a rubber band, it does not snap. Instead, when the energy in the stretched field gets high enough, the field converts that energy into a new pair of particles, a quark and an antiquark. pulled straight from the vacuum. The new antiquark attaches to the quark you were pulling away. The new quark stays with the others. The proton has effectively repaired itself, and you are left holding a new meson, a bound quark-antiquark pair, instead of a free quark. You can never win. Every attempt to isolate a quark produces more quarks. This is confinement, and it is confirmed by both theory and experiment. No isolated quark or gluon has ever been detected in open space. Every quark and gluon that has ever been measured has been measured inside a larger color-neutral particle. The colored particles are permanently imprisoned. The rubber band picture works for small separations. At larger separations, the analogy becomes less accurate, but the principle holds. The gluon field between quarks does not spread out in all directions the way an electric field does. It forms a narrow tube called a flux tube between the quarks. All the field energy stays inside that tube. The energy inside grows linearly with distance, meaning every extra bit of separation costs a fixed amount of additional energy. There is no point at which the force weakens enough to allow escape. Confinement is one of the major unresolved theoretical problems in physics. The equations of quantum chromodynamics predict it. Experiments confirm it. But a complete mathematical proof of why confinement must occur, starting from the fundamental equations and ending with an ironclad demonstration, does not yet exist. The Clay Mathematics Institute listed it as one of the Millennium Prize problems, with a $1 million prize for whoever proves it rigorously. Nobody has collected that prize. What physicists do know is that confinement is connected to the same color charge properties that make gluons split and merge. The behavior of gluon flux tubes at large distances, the energy stored in the stretched field, and the formation of new quark pairs from the vacuum are all part of the same mathematical framework that describes gluon saturation and the proton interior. Every part of gluon physics connects to every other part. And the most surprising connection of all involves particles that do not officially exist in a stable form anywhere in the universe right now. They have to be created, and they vanish almost the instant they appear. The vacuum is supposed to be empty. Zero particles, zero energy, silence. Quantum mechanics says otherwise. According to quantum field theory, the vacuum is not empty. It is filled with what physicists call virtual particles, pairs of a particle and its antiparticle that pop into existence and vanish again so fast that no detector can directly catch them. The uncertainty principle in quantum mechanics permits this. Energy can be borrowed from the vacuum for an extremely short time, used to create a particle-antiparticle pair, and then returned as the pair annihilates. The briefer the loan, the more energy can be borrowed. Inside a proton, this process is happening constantly. The quarks and gluons that make up the proton are surrounded by a sea of virtual quark-antiquark pairs and extra gluons flickering in and out of existence. This sea is real. Its effects are measurable. The virtual particles contribute to the proton's total properties, including its mass, its magnetic behavior, and the way it responds to high-energy probes. When an electron or another proton collides with a proton at high energy, the probe can resolve individual particles inside the flickering sea. At low energies, the probe sees only the three main quarks. At higher energies, it starts resolving virtual quarks and virtual gluons that exist for long enough to interact. At very high energies, the probe sees the full storm, a crowded sea of quarks, antiquarks, and gluons, all contributing to the collision. This is why the gluon distribution grows so sharply at high energies. The probe is resolving more of the virtual sea. Gluons that existed for too short a time to interact at low probe energies become long-lived enough at high probe energies to be counted. The proton appears to fill with gluons as the energy climbs, but what is really happening is that the probe is reaching deeper into the flickering sea. The flickering sea is also why the proton's mass is mostly gluon energy. Confirmed calculations show that the three quarks themselves contribute only about 2% of the proton's total mass. The rest comes from the kinetic energy of the quarks moving inside the confinement potential, and from the energy stored in the gluon field, including the virtual gluons flickering in and out of the sea. Your body has mass primarily because gluon field energy is trapped inside every proton and neutron in every atom that makes you up. The gluons themselves have zero rest mass, but the energy of their interaction with the quarks, and with each other, creates the mass you feel when you pick up a glass of water. The flickering sea inside every proton is one of the most active environments in the known universe. And this sea does something else that has a specific measurable consequence that only the most powerful colliders on Earth can study. At extreme energies, the sea gets crowded enough that something exotic can form inside it, something that should not exist in stable matter, something that MIT researchers found for the first time in 2021, hiding inside the quark-gluon plasma. Inside the quark-gluon plasma produced by heavy ion collisions, a team at MIT found something in 2021 that had been predicted, but never directly detected. Exotic particles called X-particles. X-particles are made of 4 quarks instead of the usual 2 or 3. A standard meson has 1 quark and 1 antiquark. A standard proton or neutron has 3 quarks. X-particles, sometimes called tetraquarks, have 4 quarks bound together. The combination creates a particle with properties that differ from anything in ordinary stable matter. Under normal conditions, X-particles cannot exist for long. The strong force pulls the 4 quarks into 2 pairs almost instantly. Each pair forms a standard 2-quark meson, and the X-particle dissolves in a time so short, it has no practical comparison to everyday experience. In ordinary matter at ordinary temperatures, X-particles appear for a flash and disappear before doing anything of consequence. But inside the quark-gluon plasma, conditions are different. The plasma is so hot and so densely packed with free quarks and gluons that the normal process of pair formation is suppressed. The 4 quarks inside an X-particle cannot easily find partners to break off into mesons because the surrounding medium is already saturated with quarks and gluons in a strongly interacting liquid state. The X-particle survives slightly longer, long enough for the MIT detector to catch its decay signature. The detection is confirmed. The team published their results. This was the first time X-particles had been observed inside a quark-gluon plasma. Their existence inside the plasma adds a new tool for studying the medium. The rate at which X-particles form, survive and decay depends on the properties of the surrounding gluon and quark environment. By measuring that rate, physicists can probe conditions inside the plasma that other measurements cannot reach. This matters for gluon physics specifically because the quark-gluon plasma is a gluon-dominated medium at its earliest and hottest moments. The gluons thermalize first. They reach equilibrium before the quarks do. The conditions X-particles experience inside the plasma are shaped largely by the gluon environment around them. X-particles are a probe of that environment, an unexpected one, and their discovery adds to a growing list of tools physicists have assembled to study what gluons do at extreme densities. Each new tool reveals another facet of a system that keeps turning out to be stranger than expected, and the strangest facet of all may be the one that connects everything discussed in this video back to a moment that happened before any proton, any nucleus, or any atom existed. Pick up a rock. Feel its weight. Now consider what you are actually holding. The rock is made of atoms. The atoms are made of electrons orbiting nuclei. The nuclei are made of protons and neutrons. The protons and neutrons are made of quarks held together by gluons. The quarks themselves are almost massless. The 3 quarks inside a proton carry only about 2% of the proton's total mass. Everything else, the other 98%, comes from energy, specifically from the kinetic energy of the quarks moving inside the confinement potential, and from the energy stored in the gluon field. This is confirmed. Physicists calculated the proton's mass from first principles using quantum chromodynamics, and the result matches the measured value to within a fraction of a percent. The calculation shows that the quarks contribute almost nothing to the mass. The gluons, despite having zero rest mass of their own, generate nearly all of it through their interactions. This happens because energy and mass are equivalent. A room full of bouncing billiard balls moving at high speed has more total mass than the same balls sitting still. Not much more, but measurably more. Inside a proton, the gluon field stores an enormous amount of energy in a space smaller than any billiard room you could imagine. That energy, compacted into a tiny volume by confinement, shows up as mass. The gluons are massless. The quarks are nearly massless. The proton is not massless. The mass comes from the energy of the interaction, stored inside the confinement potential and distributed through the virtual sea. This means that almost everything you have ever picked up, pushed, or stood on has its mass because of gluon energy. Every proton, in every nucleus, in every atom in your body, weighs what it weighs because of the strong force interactions between massless gluons and nearly massless quarks. The rock feels heavy because gluons are doing their job. This is one of the most striking results in modern physics, and it remains underappreciated outside the field. The origin of mass is usually described as coming from the Higgs field, which gives quarks and electrons their small individual masses. That is true, but the Higgs contribution to the proton's mass is small. The dominant source of mass in ordinary matter is gluon energy inside the confinement potential. Understanding gluons means understanding where most of the mass in the universe comes from. And that connection reaches all the way back to the beginning, because the universe began in a state where there were no protons, no neutrons, no confined quarks. There was only the hot plasma, and in that plasma, the gluons were free, not permanently free, but temporarily unconfined, moving as part of a liquid that filled all of space. What happened in those first moments is something physicists are still reconstructing, piece by piece, from collider data. A fraction of a second after the Big Bang, the universe was a ball of quark-gluon plasma smaller than the period at the end of a sentence, hotter than anything that has existed since, and expanding at a rate that would cool it within microseconds. In those microseconds, gluons dominated. The plasma was so hot that the quarks moved too fast to bind together. The gluons filled the space between them, interacting constantly, driving the thermalization of the plasma from a cold anisotropic state immediately after the collision into the hot, equilibrated liquid that would cool into all known matter. This process, the rapid gluon-driven thermalization of the early universe, is one of the central puzzles that gluon saturation theory was developed to explain. Here is the problem. A Big Bang expansion starts with matter moving outward in all directions simultaneously. The early universe was not, at the very first instant, a smooth thermalized liquid. It was a rapidly expanding collection of particles moving primarily outward, anisotropic, meaning the motion was organized in one direction rather than random in all directions. For the plasma to become the near-perfect liquid that collider experiments later reproduced, something had to convert that organized outward motion into random thermal motion extremely fast. Gluons are the answer the theory provides. In the saturation framework, the very early universe was filled with an extremely dense gluon field called the color glass condensate. This is a theory, labeled as such because the dense, slow gluon fields inside fast-moving nuclei behave like a kind of glassy, disordered solid in the mathematical description. The color glass condensate model describes the state of matter before the plasma forms, when the gluon density is at its maximum and the saturation regime fully applies. When two regions of color glass condensate collide, as they did in the early moments of the Big Bang, the gluon fields interact and rapidly transfer energy from organized outward motion into random motion. Thermalization happens quickly, driven by the strong gluon interactions of the saturated field. The near-perfect liquid emerges within a tiny fraction of a second. This model is consistent with the collider data from heavy ion collisions, where thermalization also happens extremely fast, far faster than a weakly interacting gas model would predict. The same gluon saturation physics that explains the early universe behavior also explains why heavy ion collisions thermalize so fast in the laboratory. Confirming the color glass condensate model in detail requires the same measurements that confirm saturation generally. The electron-ion collider will provide those measurements. When it does, it will simultaneously illuminate the proton's interior and the first moments of the universe. The two questions have the same answer, hidden inside the same gluon physics. Every force has a range where the math works cleanly and a range where the math becomes brutal. Electromagnetism is cleanest at everyday scales and at low energies. Gravity is cleanest at large scales where quantum effects can be ignored. The strong force is cleanest at very short distances where the coupling between quarks and gluons becomes small enough to calculate term by term. This clean regime has a name: asymptotic freedom. It was discovered in the 1970s, earned its discoverers a Nobel Prize, and explains why quarks inside a proton behave almost like free particles when the probe is very short. The strong force gets weaker at shorter distances. The coupling shrinks. The calculation becomes manageable. At longer distances, the opposite happens. The coupling grows. The strong force becomes stronger as the distance increases. This is the regime of confinement, where the math becomes extremely difficult and where most of the interesting gluon physics lives. At very high gluon densities, a third regime emerges, the saturation regime. Here, the gluon field is so dense that the usual tools for calculation break down again, but for different reasons than confinement. The gluons overlap and interact with each other so frequently that treating them as individual particles no longer works. They have to be treated as a collective field. In this third regime, new mathematical tools are required. The color glass condensate framework is one of them. Asymptotic symmetry arguments are another. The gluon scattering amplitudes, including the newly recovered non-zero collinear result, are a third. All three sets of tools are being developed and tested simultaneously by physicists working on the hardest edges of quantum chromodynamics. This triple regime structure of the strong force, asymptotic freedom at short distances, confinement at long distances, saturation at high densities, makes quantum chromodynamics the most mathematically challenging of the four known forces. No other force has three distinct calculational regimes with different tools required in each. The fact that physicists have made the progress they have, producing a theory that matches experimental data across all three regimes, is one of the great intellectual achievements of the 20th and 21st centuries. The fact that the saturation regime is still only partially confirmed is a reminder of how much work remains. And the remaining work is anchored to questions that have been building throughout this entire story. Questions that the field has been circling for decades, getting closer with each generation of experiment, but not yet answering. Those questions sit in a specific list, a short, brutal list of things that the best physicists in the world admit they do not yet know. Science is most alive at the edges of what it knows. The center of gluon physics is well established. The strong force exists. Gluons carry it. Quantum chromodynamics describes it. The proton has a gluon interior. Saturation must exist. The quark-gluon plasma is a liquid. These are confirmed facts, built from decades of experiment and calculation. The edges are a different story. The first open question is the saturation boundary. Physicists know saturation must happen. They have strong evidence that it is happening in heavy nuclei at current collider energies. They do not know the precise energy and nucleus size at which saturation fully sets in. The saturation scale, the number that defines the boundary, has not been directly measured. Every current number is an estimate from indirect data. The electron-ion collider is designed to measure it directly. Until then, the boundary is unconfirmed. The second open question is the three-dimensional interior of the proton. The momentum distribution of gluons has been measured with reasonable precision. Where those gluons are located inside the proton has not been mapped. The spatial distribution, which connects to the flickering models and the saturation geometry, is largely unknown from direct measurement. Models predict it, data do not yet confirm the predictions in detail. The third open question is the small collision debate. Whether the organized flow seen in proton on nucleus collisions comes from quark-gluon plasma droplets or from gluon geometry has not been settled. Both explanations remain viable. The measurement that would cleanly separate them has not been made. The fourth open question is the full mathematical proof of confinement. The strong force confines quarks and gluons. The equations predict it. No rigorous proof from first principles exists. The Clay Mathematics Institute's Millennium Prize sits uncollected. The fifth open question, and perhaps the most profound, is what the connection between gluon saturation and asymptotic symmetry means physically. The mathematical link is confirmed. Whether it reveals something deep about the unification of forces, about quantum gravity, or about the structure of physical law at its most fundamental level is entirely unknown. These 5 questions are not obscure technical details. They are gaps in humanity's understanding of why matter holds together, why the universe has the structure it does, and what the rules of nature look like at their most extreme. Every collider result, every theoretical breakthrough, every tool that gets built moves humanity closer to those answers. And the next generation of tools is closer than it has ever been. The electron-ion collider will answer many of the questions that current machines cannot. It will map the gluon interior. It will measure the saturation scale directly. It will weigh in on the small collision debate. It will test the asymptotic symmetry connection with real data. But the history of physics says clearly, every answered question opens 3 more. The electron-ion collider will push the saturation boundary into focus. If it finds that saturation begins at a specific and measurable energy scale, the next question is what the physics looks like deep inside the saturated regime, far beyond the boundary, at densities so extreme that even the color glass condensate model needs refinement. Accessing those conditions requires even higher energies than the electron-ion collider will reach. Future machines are already being discussed in the physics community. A higher energy version of the electron-ion concept is one direction. A muon-ion collider, using heavier leptons for even more precise probing, is another. Each proposed machine comes with a different set of trade-offs between energy, luminosity, and the types of measurements it can make. The artificial intelligence angle also points toward a different future. The 12-hour reasoning session that recovered the non-zero collinear amplitude was an early demonstration of what sustained machine reasoning can find in problems that human attention has passed over. The community is actively exploring how to use these tools more systematically. Problems that require checking vast numbers of configurations or sustaining calculation across many interdependent constraints are exactly the kind where machine reasoning can complement human intuition. The combination of new machines and new computational tools is expected to transform gluon physics over the next 20 years. The electron-ion collider data will generate constraints that current theoretical tools cannot fully exploit. Machine reasoning systems guided by human physicists will help develop and test new theoretical frameworks against that data faster than any previous generation of physicists could manage. The story of gluons is accelerating. The questions are getting harder, the tools are getting sharper, and the answers, when they arrive, will not stay confined to nuclear physics. Understanding gluons at the deepest level means understanding the strong force at its limits. Understanding the strong force at its limits connects to asymptotic symmetry, which connects to gravity and quantum field theory at extreme scales. The chain of connection runs from the inside of a proton to the structure of space itself. Every gluon and every proton in your body is part of that chain. Stand back for a moment. Everything covered in this video circles around one set of particles so small that the most powerful microscopes ever built cannot see them directly. Particles that have never been observed in isolation, particles that are permanently confined inside larger objects and can only be studied through the secondary effects they leave in collision debris. And yet those particles, the gluons, determine nearly everything fundamental about the matter that makes up the visible universe. They give matter most of its mass through the energy of their interactions. They confine the quarks that would otherwise fly apart and dissolve every nucleus. They drove the thermalization of the early universe from an expanding storm of particle motion into a near-perfect liquid that cooled into all known structure. They carry the strongest force in nature. They multiply, merge, saturate, and produce emergent behavior that ranges from individual proton properties to the large-scale organization of matter across cosmic scales. And physicists still do not fully understand them. The gaps are real, the saturation boundary is unconfirmed, the three-dimensional interior of the proton is unmapped, the small collision debate is unresolved, confinement is unproved, the physical meaning of the asymptotic symmetry connection is unknown. A formula that everyone treated as zero turned out to carry information that the field had missed for decades, and it took a machine 12 hours of reasoning to find it. These gaps matter beyond particle physics. The mass of ordinary matter depends on gluon physics. The behavior of the early universe depends on gluon physics. The structure of the strong force at its limits, and what that structure might reveal about deeper unification of physical laws, depends on gluon physics. If the electron-ion collider confirms saturation cleanly, maps the gluon interior directly, and resolves the small collision debate, it will represent the most significant advance in understanding ordinary matter since the discovery of the quark structure of the proton in the 1960s. That is the scale of the potential payoff. Not a refinement, a rewrite. The rewrite has already begun. The liquid plasma result rewrote the early universe picture. The flickering gluon models rewrote the proton picture. The non-zero collinear amplitude rewrote a calculation that had been treated as solved. Each chapter in this story is a rewrite of something the field thought it understood. What gets rewritten next is the most exciting open question in nuclear physics today, and you are living through the period when the answer is being found. A single gluon lasts for an unimaginably short time inside a proton. It fires between quarks, carrying the strong force, then is reabsorbed. It splits into two, which split again, which merge back. The whole dance happens in a space smaller than a trillionth of a millimeter, in a time so brief that no clock could ever measure a single exchange. And yet remove those gluons and everything collapses. Every proton and neutron in every atom, in every molecule, in every cell in your body holds together because of gluon exchange. The nuclear forces that power the sun, that fuse hydrogen into helium across billions of years, depend on the same gluon-driven strong force. The elements heavier than hydrogen were forged inside stars and supernovae, in environments where nuclear physics driven by gluon behavior determined which elements could form, and in what abundances. The periodic table is a gluon story. The history of the universe from the first microsecond onward is a gluon story. The quark-gluon plasma that filled all of space before any proton existed. The thermalization that turned that plasma into a near-perfect liquid. The cooling that condensed that liquid into the first protons and neutrons. The nuclear reactions that built the elements. The stars, the planets, the chemistry, the biology, all of it downstream from gluon physics. And here, at the frontier, physicists are discovering that gluons are stranger than their already strange description suggests. The proton's interior flickers instead of sitting still. The gluon field saturates at a boundary that has been predicted for decades and is finally coming into measurement range. A formula that everyone filed away as zero turned out to contain structure that 12 hours of machine reasoning could find, and human physicists could confirm. The link between gluon saturation and the deepest mathematical symmetries in physics has appeared unexpectedly, pointing toward connections nobody had planned to find. The field is alive, The questions are hard. The tools are advancing faster than at any point in the history of nuclear physics. The electron-ion collider will begin producing data in the mid-2030s. When it does, it will carry decades of theoretical predictions into direct experimental contact with the gluon interior for the first time. The saturation boundary will become a measured fact instead of an estimated one. The three-dimensional image of the proton's gluon storm will exist as real data instead of a model prediction. And somewhere in that data, physicists expect to find surprises. They always do. The history of gluon physics is a history of the data refusing to behave the way the simplest prediction said it would. The liquid instead of the gas. The flickering instead of the fixed interior. The non-zero amplitude instead of the settled zero. The next surprise is already waiting inside a proton somewhere, in a gluon configuration that current tools cannot resolve, in a regime that current machines cannot reach. Humanity is building the machine to go find it. The gluon is the most important particle most people have never heard of, and the story of what it does and what it means has only just begun.